In number 10, we notice that there's a common factor of 2 that goes into all three terms. So I will divide that 2 out. I will have 18x squared minus 9x minus 2, and I will leave that 2 out front when I split this up yet again. Now I don't know how to break down the 18, but I notice that 2 is prime. So I'm going to have a 1 times 2 that's guaranteed, and then I'm going to switch to my pencil here, in my case the red pen, and try the different combinations of 1 and 18, 18 and 1, 2 and 9, 9 and 2, 6 and 3, 3 and 6, until I find the right combination, and it turns out that it's going to be 6x and 3x. My outer becomes a 12x, my inner here is a 3x, and if it's a positive 3 and a negative 12, that will then make the minus 9x that I'm looking for. And you can check this all by distributing it back together and verifying that you get back up to the top line here. In number 11, I have no GCF, but I notice 5 is a prime number, and that's a good clue to me because I know this is going to end with an n and a 5n. And then I've got to figure out how to break up this 12. Since 11 is right around the same value as 12, I'm going to try a balanced approach of 3m and 4m, and I'm being brave doing this in pen here. Let's check what's going to happen. I'm going to have a 4mn in the center and a 15mn on the outer, and if I have 15 minus 4, that will make the 11, and yes, I do want that to be a minus n and a positive 5n in the second parentheses. For number 12, I noticed that 4x times 4x makes 16x squared, 3 times 3 makes 9. I wonder if I can factor this into 4x and 4x plus 3 and plus 3. That would be a nice way to go. My inner would be a 12x, my outer would be a 12x, and yes, those do add up to make 24x. Now, since this happens somewhat frequently, it's worth checking for that. We're going to rewrite this as a binomial square, 4x plus 3, quantity squared. For this next problem, I have a p to the fourth. Okay, I've got to play around with this somehow. First thing I want to do, especially since the numbers are somewhat balanced, is try a 2p squared, 3p squared approach. And then I would try 1 and 10, 10 and 1, 2 and 5, 5 and 2, but would find out that none of those actually work. So I'm going to cross that out and switch gears here and go to p squared and 6p squared. Then I would try all those numbers again and find out that plus 2 and plus 5 actually work because I get a 12p squared and a 5p squared, which add up to the 17p squared that I'm looking for. So it's worth your time to just try this trial and error. Eventually it will come out, and if it doesn't factor at all and you've tried all the combinations, it's possible that this isn't a prime expression and you would write prime as the result here. Next problem, I noticed that y goes into all three terms, so divide a y out. That leaves me with 3y squared minus y plus 12. And since 3y squared, 3 is prime, I'm going to rewrite this as 3y times 1y, and then play around with the different combinations, hoping that I can make this work. Now I try 1 and 12, 12 and 1, 2 and 6, 6 and 2, 3 and 4, 4 and 3, but none of them work at all. And so basically, that's not going to factor any further. I don't say this is not factorable. I did factor the problem. I took out a greatest common factor. And that's as far as that problem will go. And that happens occasionally. So just be aware, and that's what kind of adds to the frustration of these types of problems. But also, if looked at another way, these are puzzles, and you can kind of have fun with them.